Okay, welcome to Properties of Exponents. Let's jump right into it. We're looking at this standard form of an exponent. We've got the base is 5, the exponent is 7. That means 5 times itself, 7 times 5 times 5 times 5 times 5, and so forth. Okay, pretty large number. We're going to look at some properties of dealing with bases and exponents, and we're going to start with this for multiplication. If the base is the same, then you're going to add the exponents. And here's the example: 4 to the third times 4 to the 7th equals 4 to the 10th. And where are they getting that? Well, 4 to the third is the same thing as saying 4 times 4 times 4, and then 4 to the 7th is so times 4 times 4 times 4 times another 4 times another 4. I've got 3, 4, 5, 6, and 7 of them. Well, in all I have, excuse my bad handwriting, 4 times 4 times 4, so I've got 10 of them, okay? And that's where they're coming up with this shortcut of if the base is the same, you can just add the exponents, and that's where they're getting that 10. Okay, likewise, x to the 5th times x to the 4th is x to the 9th. When we look at division, we're going to, if the base is the same, then we're going to subtract the exponents, because on top here I've got 4 times itself 10 times. On the bottom I've got 4 times itself 3 times. Well, 3 of these 4's are going to cancel out with 3 of these 4's, leaving 7. So the shortcut is going to be to subtract them. X to the 15th divided by x to the 3rd is x to the 12th. Again, we're just subtracting. And then finally, for a power to be raised to another power. So if you take the exponent and raise it to another exponent, then what we're going to do, well, look at this. You can see the 7 and 3, we've multiplied those to get to the 4 to the 21st. Well, 4 to the 7th raised to the 3rd power is kind of like saying 4 to the 7th times 4 to the 7th times 4 to the 7th. And if you go back to our rule that we just learned up here, for multiplication, if the base is the same, you keep the base and you add the exponent. So look at that, 7 times 7 times 7, I'm sorry, 7 plus 7 plus 7 is 4 to the 21st. And I could have written that out in the long way, I won't do it, but 4 times itself 7 times, times 4 times 4 times 4 times, so forth, 7 more times, and 7 more times. There would be 21 4's in that list, and no one wants to do it that way, so we just go with these shortcuts. X to the 5th raised to the 2nd power equals x to the 10th. You're going to keep that base and multiply those exponents. All right, well, let's get busy with some problems. I'm going to do the first one. I recommend that you pause it after that, do the other 5, and then check and see if you got the right answers and listen to the explanations. All right, so the first one, I'm going to take these coefficients out here. We haven't seen this before, and I'm going to pull them out separately. So this is 2 times 3 times 2, and I still have the x to the first. I know there was no exponent on that, but that if there is no exponent, it is to the 1st power, times x to the 3rd times another x to the 3rd. So all I did was kind of rearrange these variables in their exponents, and that's using the commutative property of multiplication, just rearranging everything. So 2 times 3 is 6, times 2 is 12, and then all the x's, I'm keeping the bases and adding the exponents, so it's 12x to the 7th. All right, again, I would recommend pausing it, trying these. I'm going to go kind of fast, so maybe you can check them after you try it. So pause it at this point. This is 2n squared times n to the 1st. So it's to keep the base of n and add the exponents to it, 2n to the 3rd. The next one is 3a to the 6th. Again, we kept the base of a and added the exponents. Over here we've got 2 times 2, so I'm going to pull that out separately, is 4. Those are not exponents, those are just coefficients of the bases. And then I've got k, keeping the k, adding the exponents, I come up with 2. Now some people know that anything raised to the 0 power is 1, so that k to the 0 can be replaced with a 1. All right, which basically effectively cancels it out, because 2 times 1 is still 1, so you're still left with a k to the 0. All right, and last two here, 3x squared, because these are 1's, keep the base, add the exponent. Here I'm going to do that rearrange like I did in the first problem. 2 times 2 is 4, times 3 is 12. Rearranging, and I've got x squared, x third, x 0. Keep the base, add the exponents. I've got 12x to the 5th. All right, how'd you do on that? Moving forward, we got those were all multiplication problems. Now we're going to look at raising the power to a power. All right. Because of these parentheses, this 4 gets applied to both the n to the negative 2 and the 3. All right. So I'm going to, this is like, it's effectively like saying 3n to the negative 2 times itself, times itself, times itself, and 4 times because that was the exponent. So you can see as I build this that we've got how many 3's being multiplied? Well, 1, 2, 3, 4. So I've got 3 to the 4th and n to the negative 2 raised to the 4th power. And when you do that, when you raise an exponent to an exponent, you multiply the exponent. So I've got 3 to the 4th times n to the negative 8th. Now we haven't talked about negative exponents, but I want you to notice that the answers here it's saying should contain only positive exponents. So how are we going to deal with that? Well, if you see a negative exponent, you take the exponent and its base, the n, and you're going to move it to the denominator. Alright, so I still have 3 to the 4th on top, and I've got now n to the positive 8, and I'll give a little explanation on that in just a second. 3 to the 4th, if I multiply that out, 3 times 3 is 9, times 3 is 27, times another 3 is 81. So this is 81 over n to the 8th power. Okay, so negative exponent, move it to the denominator, and it becomes positive. Quick explanation, 10 squared, most of us know is 100, that's 10 times 10. I am putting a decimal there. 10 to the 3rd power is 1,000. I'm going to kind of write it the same way, moving the decimal out, okay? But if we go the other way, 10 to the 1st, and we're still doing that kind of move the decimal concept, it's just moving the decimal over left. So 10 to the 0, a minute ago I said 10 to anything to the 0 power was 1. Look at this, continuing this pattern of moving the decimal over. 10 to the negative 1 is, well, continue this pattern and you'll get 0.1, or we say that as 1/10. In a lot of cases that's 1/10 to the 1st. See what happened? 10 to the negative 1 is the same thing as 1 over 10 to the 1st. I didn't have to put that to the 1st there, but you can see that a negative exponent, if you just put it down in the denominator, becomes positive. So if we encounter a negative exponent in the denominator, we're going to move it up and it will become positive at that time. All right, let's continue with this. 4, and you might want to pause this at this point and try some on your own, but I'm going to apply the 4 to both of those. So that's 3 to the 4th and m to the negative 16th because I had to multiply those exponents. Simplifying that further, that becomes 81 over m to the 16th. I was applying that, take the base and its negative exponent, move it into the denominator, at which time it becomes positive. Again, here I'm going to apply the 4 to the p to the 4th and to the 2nd, so I've got 2 to the 4th, p to the 16th. I multiplied those exponents. 2 to the 4th could be written as, well, it's 2 times 2 times 2 times 2, which is 16, so it's 16p to the 16th power. All right, and then finally, this one was the easiest one. I should put this at the beginning. X to the 3rd to the 4th. You multiply those exponents, x to the 12th. All right, we got 2 more like these up here, 11 and 12, so I'm going to go ahead and do those before I start talking about the division ones. Again, I'm applying this 2 to both of these, so it becomes 4n to the 6th power. I was multiplying those exponents. Here I've got 4 to the 3rd, as we saw, well, no, we haven't, oops, not equals. 4 to the 3rd and b to the negative 3rd. I do want to simplify this further. 4 to the 3rd is 64. That's 4 times 4 times 4. And then b to the negative 3rd, I want to make that positive by moving it down into the denominator. That's my final answer. All right, now division. If I want to use the division rule, for division, if the base is the same, then I'm going to subtract the exponents. All right. That does not apply to these coefficients out here. 3 over 2 is still 3 over 2. Some people might call that 1.5 or 1 1/2. All right, but now I'm going to look at this. I've got r to the 3rd over r squared. I'm going to keep the base, subtract the exponents. 3 minus 2 is 1. I could rewrite that as 3r over 2. That's my final answer. So I kept the base, subtracted the exponents. Here again, the coefficients, I don't do that rule with the coefficients, just bases and their exponents. x, I keep the base, I subtract the exponents of 2 minus 3. Ooh, that comes out to a negative 1. What did I say about negative exponents? We're trying to write these all in positive, so I'm going to move that down to the denominator, at which time it becomes positive. So it's 2 over 3x to the first, or just plain 2 over 3x. That's the best way to write it. Right here I've got 4/3. Again, those coefficients aren't doing anything. I've got n squared. Where did I get that? N to the third minus, I'm subtracting these exponents. Whoops, missed that. Subtracting those exponents. 3 minus 1 is 2. That's my final answer. And then here I got a 3 divided by 3 is just 1. So those effectively cancel out. It's just 1. And I've got a squared divided by a. Well, that's an a to the first. So I keep the base, subtract the exponents, 2 minus 1, which is just a, or a to the first, which is just a. And that's it. All right, have fun with those. See you in the next video.